by Spry. This time we're going to have a look at solid simplification. Last week we were going to have a look at it, but then we realized there was a few options that we needed to add to the new algorithm to make it work better. So the new version that came out today has those improvements, which means that we can get to it. So I'm going to start with simplifying. We'll talk about simplifying solids. We're really talking about simplifying any three-dimensional object. So that includes triangle meshes, polygons, polyhedrons, things like that. We're going to start with simply discussing the default settings and a couple of things you're going to play around with. So I've right-clicked this particular triangulation, and I'm going to simplify it using point collapse. We'd recommend there's another algorithm coming soon, but point collapse will be the default. We'll untick overwrite so that we keep our existing one, just so we can compare the results, and we can actually try a few different results each time. So a couple of other minor changes to this previously. If you hit simplify, you would be stuck with whichever options you picked regardless of the outcome. So if you're not happy with the amount of simplification that's gone on, you would have to reopen the menu, rerun everything. Now you can just change the settings and re-hit simplify. So this particular triangulation takes, about 10 or 15 seconds to simplify, and you can see here that with the default results, we've gone down from 1.1 million triangles to 900,000. The biggest difference that you're going to make with this particular algorithm, given that you leave the advanced settings alone, which I'll discuss in a little bit, the biggest difference you can hit here is changing the angular tolerance. So the angular tolerance just refers to how essentially this is how much simplification can you try and smash out of it. And so I'm going to accept this change, and I'm going to run one more simplification so you can see the difference between the two triangulations as they get done out. So I'm going to set that to the maximum, which is 45 degrees. You'll note that I can't increase the angular tolerance any more than that. Sorry, I was just getting a warning from YouTube saying something about my stream, but it's still working, so we're going to leave it. I'm going to hit it at 45 degrees instead, and I'll show you the difference between the two. I've left it set to overwrite, which was a mistake, but I don't have to hit accept, but I will in this particular example, just to show you the two topographies side by side. So you'll see now that with it set to 45 degrees, my simplification is now quite a bit more. It's 2/3 smaller than it was before. So I'll just accept that, and then I'll load up both topographies. And show you the difference. Okay, so the more heavily simplified triangulation, going to fire that off one more time. I'm just going to make sure that has actually gotten saved correctly. We'll accept that one. Yeah, it has. Okay, so it's been simple. We've just extra simplified it this time around. There's still so many triangles in it that it's a little harder to tell. So let's have a look at the two different ones. So we've got, this is the one with the 45 degree angle tolerance, and you see here, it doesn't mean much to you, it's not your triangulation, but if we have a look at the one that has a much lower angle tolerance, you can see that the triangles have been maintained. This was the original, sorry I didn't show you what the original triangulation looked like, but this is a more, very, very close to what the original triangulation for this particular mesh looked like. And then I'm going to make one other change to the way that this is working. So we'll have a look. This is the existing one that was set to 45 degrees, still simplified, but still, hundreds of thousands of triangles. I'm going to make one other change to a simplification. I'm going to run it one more time. And this time I'm going to increase the planar tolerance. This is a distance, so a number of meters. You don't have to know particularly well exactly how the algorithm works. If you want to know, we can point you at some papers and things like that on how point collapse algorithms work. But if we set it to 5 meters instead of 0.5 meters, we get a much heavier reduction. And what that means is it sort of has greater tolerance for how many points can actually get moved around. Essentially, how far can a point get moved is the planar tolerance. So a point can only be moved a maximum of 0.5 meters in the defaults. Now that we've moved it a maximum of 5, and I have a look at that outcome, you can see a much more heavily simplified topography. Now, in order to get results that match what how important the result is, I suppose the key thing that I'll say with solid simplification, in particular for triangulations, the simplification of triangulations, is that if you plan on using this triangulation to do a relimiting or an initial state, don't simplify it at all. And what I mean by that is you can't guarantee the accuracy of the final value. Like it will be very close, but if you're trying to do things that are volumetrically accurate, you should be leaving these in their original state. However, if you're loading them up to run animations on, obviously the fewer triangles you have on screen, the faster everything's going to run. And so if you're running your solids, you've got your images, it's going to run much faster with a heavily simplified triangulation. And when you've got the image on, a lot of the time, you're actually not going to be able to tell that what you've got has been heavily simplified. Like if you can tell the difference visually up here between the original and the simplified one, you're doing better than I am. They're going to look virtually identical. So for triangle meshes, really, you can set them to be quite aggressive as long as you're happy with... Give that a second to load the image. So there's the one. You can see even as I rotate around in this particular example, it's a little sluggish. If you might not be able to see the number of frames per second, but if I load up the other one, this is also partially to do with me running YouTube, but you can see that the performance of this one's much faster. So that plays a role as well. This is why we're doing solid simplification, is to try and make our animations perform better. So that's simplifying triangulations. Now, in terms of simplifying your solids, the general rule of thumb here is with the new simplification algorithm, I would recommend you keeping your original solids in an imported section and then having your simplified solids live either next to the imported solids or in a separate folder that's called simplified solids. The reason for that is you may want to refer back to your original solids to cut them using the relimiter. What we're going to be doing with the solid simplification, we'll try to maintain the volumetric integrity of the solid, but once again, it's more, you should consider a simplified solid an animation solid, not a volumetric solid. So I'm going to show you a few different ways or a few different sets of options, and we'll talk about the advanced options now. So this is what was missing last week in terms of discussing how we can best do solid simplification, but when we go to the solid simplify solids menu, what we're looking to do is we click on the solid that we want to simplify, and then we say where we want to target it. So almost always, and I would recommend this very strongly, is you don't overwrite your existing solid. You would only do this in the rarest of circumstances. You are better off maintaining the original solid. It does hold some space in your database, but if you're not using it for the animation, that's all it really does. It makes your file size a bit bigger. It shouldn't affect, and it won't affect your load times of your models. It may slightly affect the save times of your models, but only by a little bit. It really, unless you're running out of hard drive space, in which case I'd tell you to go and buy a new hard drive. So in this example, what I would say is, yeah, you don't want to overwrite the existing ones because you may want to fall back on them. But you may, if you're doing relimited solids, maybe then if the relimited solids, you want to simplify those, you can overwrite those. But coming back to the stuff that was missing last week, which is what's been added in for the new algorithm, is this volume shift series of settings down here. So the way that the algorithm works now is we will run the solid through the settings that you've chosen. So if you say 10 degrees, 0.5, these numbers may not mean anything to you as a first pass. We've done a bunch of testing in terms of what is, 80% of the time it gets a decent result for the amount of time it takes to actually do it. These settings are a decent place to start for normal open cut style solids. If you want to be more aggressive, you bump up these numbers, but what we'll do now is if the volume shifts more than the tolerance that has been set, so in this example it's a 1% tolerance, if the volume shifts more than that, what we do is we fall back on these iterate, count limit, and iterate factors. And to explain that as simply as possible, what we do is we iterate the number of times that you put in here. If you put in 1, it will just not accept the result. If you put in 2 or 3 or more, each time what it does is it multiplies your planar tolerance by the iteration factor. So if we start out, to make the maths a little simpler, if we start out at 1, it multiplies it by 0.25. So the next planar tolerance that it will try is 0.25. The next planar tolerance it will try is like 0.825 or something like that, whatever the maths is for that. And it will try up to 4 times. So it will multiply that number 3 times, essentially, the number of iterations it will do. So testing a different planar tolerance each time. It's not changing the angular tolerance. So if you don't get a good enough result from this first pass, and I'll fire off a pass now, if you don't get a good enough result from the first pass, then your options to change, my suggestion would be, is that you can bump up the planar tolerance a little bit. So I probably should have shown you the results of that. We'll run it one more time. The settings should have been saved, so I should just be able to hit run again. So the results of this particular one gives me a reduction of about 70%, which is for animation purposes. You know, the reason why we simplify our solids is our graphics cards have a finite amount of memory on them, and once you go over that in terms of how many solids are on the screen, then your graphics will slow down significantly. That's really the big one. So that was at the default settings with everything set to default. If I want to try and increase the amount of simplification that goes on, I can increase the angular tolerance, go through, write this to one of the alternate fields, and I'll just show you the results. You'll still get, this one will be slower. The reason why running a higher angular tolerance will be slower is going to be because it's more heavily simplifying the solids, and so it's going to hit that volume tolerance faster, which means it needs to iterate more times. The way the iteration works is, so you can see we got more simplification out of it, which is what you would expect, but not, you know, it was 70% before, now it's 78%. It's not changing that much differently, considering the amount of extra time that it took, and the big change in the actual angles that it's allowed to move. Now, if we change the volume shift and run it one more time, my expectation is that it will be faster because it's allowed to shift more volume, and also that the amount of simplification that actually occurs will be more. So we can more heavily decimate the solids if we're allowed to shift that volume more. So we're at 78%. If we allow a 5% volume tolerance, we're now at still 78%. So it's in this particular example, either the solids get decimated a lot, or they don't get decimated at all. So some other options that you might want to do then is, if you really you're happy to set it to be to fire it off and totally forget about it, what you might want to do is, and we'll write this to the last of the fields, is you might want to set your planar tolerance to be really high, set your angular tolerance to be as high as it gets, and then you just increase the number of iterations that you allow and increase the iteration factor, as in the closer you get to 1, the number of times it's going to test different planar tolerances. So this one will take it'll take a decent amount longer than the previous runs, but it should still be reasonably quick, because what is happening is, if it successfully reduces the size of the solid and doesn't hit that volume tolerance, then it won't do the 10 iterations, it'll just do the first one. So it's only going to be slow if you're giving it things that it definitely can't achieve. So 78% was the best before this. When we run it at those settings, we are up to, so this one's telling you that none of those work. We're up to 80%, but you can see diminishing returns pretty quickly. The first version that we had, where the settings were default, was 71%. And if we open up the table quickly as the final thing that we'll do today, and have a look at any particular record on the table, let's start with one of these, where are we? One of these triangulations. You can see that you can see the number of triangles, what we start with and what we finish with. So here's the original solid. Here's the default simplified solid, looking pretty similar. Here's the most heavily decimated solid. You can see now, especially if you're looking in the areas of detail, you can see around here in the original solid, or even the less simplified solid, you can see a little bit more detail around the edges. So it's still maintaining the shape, right? Which is kind of it really comes down to how important is that small amount of detail. That planar tolerance factor really plays a big role in your thinner solids. So if you're looking at things like coal, and we haven't actually run any simplification on the coal this time around, but that's where it can play a pretty big role as well. So you can see here that even no matter what settings we set on this simplification, the results are always the same. So to summarize, recommendations are, as a first pass, create separate solid fields for each of your solids that you're currently running. Use them, call them animation or simplified solids. Don't overwrite your original solids. If they're not being used in the animation, then they're not going to do any damage. The one thing that I haven't shown you, which I'll show you now, is how do you actually make sure they get used. So the way this solid simplification system works is if something doesn't succeed in simplification, we do copy it down into the field, into the new solid field. So you don't have to use the alternative solid fields in the process list. So what you do in the solids list to use the new simplified solids is set the simplified solid, and the easiest way to do that quickly is to set the new fields in there and then do a quick bulk edit, drag, drop, and potentially copy paste. And that now will mean that when you load the animation, you're using the simplified solids instead of the original ones. So if you have any questions about that system, if something's not working as you'd expect it to, please let us know. There's another algorithm coming sometime in the next couple of weeks which does a slightly different method to simplify solids. So you may be mixing and matching depending on the style of simplification you're chasing. I hope that was informative, and if you have any questions, as always, let us know, and have a great weekend.